The broadcast is now starting. All attendees are in listen-only mode.
Hi, everybody. Thanks for joining us this evening. Although I can't see it from where I'm currently sitting, hopefully you're all staying nice and dry with the rain that I'm told we have been having or may be expecting the rest of the evening. This is Liz, one of your CTTC chairs, and I'm just going to go through a couple announcements before we get started. So this is our last meeting of our ASHRAE fiscal year. So I'm going to send a huge shout out to Fiona for such a wonderful year and the whole board, Patrick, Dave, and Chris, and everybody else who's been involved the whole year with planning and meetings and all sorts of great programming that we've had available. And then another huge thanks to Don Doherty for all of his amazing efforts getting out emails and updating the websites, and all his work with the communications. So thank you very much, Don. A couple other items for the chapter. Don is working on a newsletter that I think will be coming out at the end of June, possibly the beginning of July. Check it out to see how our year has wrapped up, and any of our events that we hope will be taking place the rest of this year. And then if you are interested in being involved, especially if you want to help planning with any of our meetings that will start back up in August or September and plan through next June of 2021, please reach out to myself or anybody on the board. You can go to the Illinois chapter website and find all of our email addresses or contact information. We'd love your input, or if you'd like to present or participate, that'd be awesome. So for this presentation today, thank you for joining us for our second webinar now. If you have any questions, we'll take breaks for questions, but you can type them into the question tab within GoTo, and then we'll break to take questions. We were not able to get polling into the question format in GoTo like we did before. So when we do a poll question, we'll just ask that you raise your hand. You can do that in your little attendees window pane, I think, and then we'll just do a quick count. And then after you raise your hands, I will close them all back down so we can take the next question. But if you have any questions or need anything throughout, you can also message the whole group through questions or use the chat feature as well. With that, we'll go ahead and get started. So Jason Greenberg and Frank Kohout are joining us today to discuss kitchen design, ventilation, and commissioning. So many of you have probably seen both Jason and Frank at other ASHRAE conferences, meetings. I believe they have both presented recently at our spring conferences in the last couple of years. But they have lots of experience both on the kitchen side and on, commissioning as well. So with that, I will let them go into a little bit more detail and get started.
All right, thanks, Liz. This is Jason Greenberg. I'm going to introduce myself, and then we'll have Frank introduce himself. Like Liz said, I'm Jason Greenberg. I'm the Chief Mechanical Engineer at MGN in Oak Terrace, Illinois. Licensed professional engineer in multiple states. Been designing restaurants for over 20 years. 10 of those years, actually 11, were spent with McDonald's USA and designing restaurants for them across the entire United States. Also been involved in ASHRAE Technical Committee 510 for the last 15 years, including 2 years as the committee chair, as well as ASHRAE Standing Committee 154, which publishes the Standard 154, and NFPA 96. Frank, I'll turn it over to you for your introduction.
Thank you, Jason. As you can read, I'm Frank Kohout. I'm a Director of Special Projects with Cyclone Energy Group. I've been doing HVAC design for close to 30 years now. I actually started my career at WMA well before Liz was there, but was a designer there for 8 years. Then went to McDonald's where I worked there for 16 years. Jason and I worked in very similar roles. He was on I started on the US side, and then I went to the worldwide side, and he started in the US side. So we worked together for almost 10 years, I believe, as partners, coming up with standards and doing design work and making sure things worked for the brand. My background with kitchen started with my involvement with TC510, which is a kitchen ventilation technical committee on ASHRAE's TC510, and then also my work on SSPC 154, which is the standards committee, which TC does all the work, including research, handbook, and things like that. The standards committee writes the standard, which can be turned into a code in that specific language. I've also been the handbook chair for 3 cycles now, starting from 2007 to 2019. After 3 cycles, that was enough. But so everything you see in the applications handbook, chapter 34, is a result of the committee that from TC510 that worked on it. Thank you.
All right, and as Liz had mentioned, we don't have polling available, but we have some questions that we want to ask you guys as part of our presentation, just to get an idea of who's out there and who's listening. You'll raise your hand in the GoToWebinar application on your screen. Our first question for you guys out there is, how many of you have designed mission critical server facilities? And I'll give you guys some time to answer that.
Just a small handful so far of 5 people.
Just 5 people, okay. So not a lot.
All right.
There's some rationale for these questions, so I'll kind of explain that while we're waiting for anybody else to respond to it. But if you've designed mission critical facilities, you're very familiar with server heat rejection and how to deal with that load. And so designing a commercial kitchen is very similar. There's a lot of heat packed into a small room, and we'll cover some of that in our presentation today. How are we doing on responses, Liz?
We were just at the 5. I lowered everybody's hands now so that we could go to our next one.
All right. Okay, our second question is, how many of you have designed clean rooms? So the rationale for this question while you're answering is air distribution in the kitchen is going to be somewhat similar to designing a clean room or a laboratory. The reality is that the less air disturbance and turbulence and mixing that you have in the kitchen, the better the kitchen performs.
Just got a few people so far.
Just got a few people on that one too. Huh. All right. I'm hoping the next question will be a few more than just a few people. So, are we ready for question 3?
Yes.
All right. So question 3 is, how many of you have designed some type of food service facility? So this could be a freestanding restaurant, could be food service inside of a hotel, or something of that nature, but or even a hospital.
Lots of hands going up now.
Lots of hands going up on that one. All right.
All but a handful.
Well, see, now I'm concerned because hopefully we'll actually teach them something new, and they don't know all this stuff already.
All right, yeah, I'd say all but Looks like 6 people or so have designed some sort of food service facility. Ready for
All right. So that's a pretty good portion of the attendees. That's great. The last question is, how many of you have commissioned a commercial kitchen? Frank, you don't get to answer this one.
5 people so far, which was more than I think our clean room and mission critical. We've got 6.
Yeah.
We're up to
Okay.
6.
I mean, I know those designers for mission critical and clean rooms happen to be very kind of specialized, and that's pretty much all they do. But figured we'd see if anybody has ventured out of those realms.
Yeah.
All right. So before we really get into the meat of this presentation, I wanted to just kind of highlight some of the stuff that we've done. Frank and I have been involved in to some degree, and then obviously what Technical Committee 510 has done for ASHRAE and for the industry for commercial kitchen ventilation. Here's a somewhat comprehensive list of all the research projects we've done over the roughly last 25 years, and I'm just going to highlight a few and explain how they've contributed to the industry as a whole. All right, so first and foremost, we have research project 623, done from 1993 to 1994, and this was the basis for UL 710. All right, so this became the standard for exhaust hoods for commercial cooking equipment. All right, and then in 96 and 2001, we had research projects 851 and 1151. And these research projects helped develop UL 1046 standard for grease filters for exhaust ducts. And then in 2008 and 2009, we had research project 1362, which collected appliance heat gain data and is the data that is published in ASHRAE Fundamentals Chapter 18. So if you guys are familiar with a chapter on heating and cooling load calculations for non-residential, all the data that's in there was done through a research project. And then the last one was kind of a longer research project because we had to collect data during the summer and winter months. And that one was from 2010 to 2013. So again, a pretty good research project in terms of length. And this was research project 1469, which was a thermal comfort study in commercial kitchens. And I'm not going to say that we shouldn't strive for 75 in a kitchen, but in reality, what we did determine was that ASHRAE Standard 55 does not really apply to commercial kitchens. It's really hard to do that with the high radiant gains and along with the latent and convective heat loads coming off of appliances. Now, that doesn't mean that we, can't try and get thermal comfort to 55, but the reality is it'd be really tough to get there. All right, so that kind of brings me into some of our works in progress. And right now we have research project 1778, which will be wrapping up very soon. We had a 6-month extension that was added on in January, so that should be wrapping up in July. And that project was to determine the heat and moisture load for commercial dish room applications and equipment. We know that those appliances and those pieces of equipment put off a lot of moisture. All right, and one of the products that's supposed to come out of that research project is a dish room ventilation design guide, which will be pretty beneficial for those of us who design restaurants, especially those with large dish rooms. And then right now, Frank and I are both involved in a commercial kitchen ventilation design guide, which will be published by ASHRAE, and we are seeking co-authors. So if anybody wants to get involved with writing some chapters or maybe being an editor of some type and just kind of, maybe learning some stuff along the way, feel free to reach out to either of us. But last but not least, we do want you guys to get involved if you're available to do so. It doesn't necessarily have to be within our technical committee. There are tons of ASHRAE technical committees out there to get involved in. So, you know, feel free to check some of that out. All right. So we're just going to do a quick let's start here, and what we have is a commercial kitchen ventilation design flow chart, kind of like a recommendation on steps to take and things to consider through the design process. So we don't get into the construction piece or the post-construction piece. So commissioning and test and balance will be covered in this presentation to some extent, but it's not part of the design flow chart. Just want to highlight some of the stuff we'll be covering today. Kitchen hood exhaust air, makeup air, pressurization with transfer air and whatnot. And then also heat gain from commercial kitchen appliances, and as well as some control stuff, but primarily around the DC KV system. So that's that second bullet point there. And that list, I mentioned before, some of the construction stuff, the test and balance, and the commissioning, which Frank will cover as part of this presentation as well. All right, and as Liz said, we'll be opening it up to questions at certain points in the presentation, and now is that time. If there are any questions that you guys have, feel free to type them into the chat box.
And you're welcome to ask your questions at any time. We're just going to convey them at certain points. So feel free to, as they come up, we'll just moderate them for our responses.
I don't see anything in the window on our end, so.
Yep, me neither.
Okay, great. All right. So we're not stumping you yet, which I didn't think you would. But again, just want to stress, if anyone wants to get involved, if you want to do some authoring and get credit on a commercial kitchen design guide, feel free to reach out to Frank or myself. All right, with that, I'm going to turn it over to Frank, and he's going to start working the presentation here.
All right. Thank you, Jason. One thing I just wanted to add on to what Jason talked about TC510 is, if you look at all the research projects, it's been an evolution from designing kitchens using rule of thumbs and anecdotal devices to actually using hard information based on independent research to come up with better approaches, more energy efficiency, better hoods, all kinds of better systems, and it continues to move on. So a lot of that is, the focus of the committee is really to advance and come up with better ways and better technology and better ideas for kitchens. So with that said, I'm going to start with hoods, which is something you as designers may not typically encounter, because typically the hood is picked out by the food service consultant. And what I want to do is I want to give you some background on some of the details of what goes into selecting a hood and some of the details behind it. And I will say that I really recommend that every engineer who designs a kitchen understand what went into the hood and feel confident enough to question some of the hood designs, because you're experts in ventilation, and sometimes the people that pick out hoods from the food service industry, they are not. I will say that they are great at laying out kitchens, they're great at what they do, but when it comes to the ventilation, oftentimes they're maybe not making the best choice when you look at an overall HVAC kitchen design. So that's why we're starting with the hood. Jason and I both know this topic very well. Everything that you will design in a kitchen and an HVAC system is based on what hood is selected. So I'm going to start with some information you might see with different hoods. If you look at a hood, if you look in on the web for a generic hood information, they will list UL numbers. And I want to talk a little bit about that, because UL numbers for airflow are different than design airflows that you will see for a specific project. And I can get into the details of that. A UL test, and I've witnessed one before, they set up one hood, they set up one appliance, not like you see in the picture here, which is more real world, but one griddle or one charbroiler, at the furthest location from the exhaust collar, which is typically at the end, and they use hamburger patties of a certain grind, which emit a certain amount of grease, and they observe and make sure that not all the smoke is captured at the airflow. And if it captures, UL will sign off on it. If it doesn't, then typically the airflow is increased. The test is repeated until it captures. So that's how a UL number is determined. What you see in the real world is typically higher than what you see in a UL number. Go ahead in the next slide, please. Before I get into that, there are different kinds of exhaust hoods. I'm going to be talking about the canopy hood, which if you click on it, Jason, will be highlighted. There's other hoods shown here. There's back shelf hoods, which are more efficient than canopy hoods. Canopy hoods are the most common you see in stores and restaurants because they're inexpensive and they work pretty well. There's passover hoods, which are closer to the food source. There's island canopy hoods, which do not have a wall around them. They're just above some cooking equipment located on an island. There's double island canopy hoods, which are 2 island canopies back to back. And then there's even eyebrow hoods, which you typically see in ovens, as shown on this picture. Go ahead in the next slide. So what's involved with the specification of a hood? You look at the type of hood. Are you going to pick a canopy, back shelf, island? This is all the selection process that goes into it. The next one is the cooking duty, which is the temperatures of the appliances. And I have a slide highlighting that because that impacts the airflow that is designed for a hood. The next item is you must have overhangs of 6 inches to the front and to the sides, unless side panels are utilized. So the hood is supposedly, unless they've got side panels, larger than the piece of cooking equipment. You can have more than 6 inches. And in fact, one of the research projects that Jason referenced, was a project where they installed hoods over 12 inches overhangs and 18 inches, and they found out that they could reduce the amount of air that was needed to exhaust. So, but the minimum is 6 inches unless you have side panels. Then you can have 0, but the intention is that you capture all the heat and smoke. That's something to look at it when you're doing commissioning too, is to verify that these overhangs have been installed, because sometimes things get moved around, things change between design and construction. So that's a critical item to look at. Will the hood incorporate demand control kitchen ventilation, or DCKV? We can talk more about that. That's the demand control that's based on cooking. I want to state this last sentence here, that the hood should capture and contain all the cooking effluent. I remember commissioning one project where we were out there watching a hood try to capture, and they were having some issues with it. And I don't know who said it, but somebody was trying to make the case that it was capturing most of the effluent and that was acceptable. That is not acceptable. It needs to capture all of it. You wouldn't design an HVAC system that mostly cools, but on some days it doesn't. The same thing with a hood. Your hood should capture all of your effluent. Last little topic here is hooded versus unhooded. I'm not going to go into a lot of detail on that because we're trying to cover a lot of topics here, but you can have unhooded appliances provided that the heat gain within the from the appliance is taken into account in the HVAC, and that it emits less than 5 milligram per meter cube of grease. So you can have small appliances that don't emit a lot of grease or a lot of heat unhooded, but for the most part, any large appliances should be hooded. And if you need more direction on that, you can reference standard 154. There's a whole listing of typical appliances that are required for hooding. Next slide, please. A little bit about the appliance type by duty and typical exhaust. What you're going to find is that you have to have different CFMs, even for the same size hood, based on what you have underneath, what the appliance you have underneath. So this is kind of a summary of a list. This is actually it's listed in chapter 34, applications, tables 4 and 5. It's a summary of both tables. You have light duty equipment, which is like ovens and steamers that typically operate at like 200 degrees Fahrenheit. The number 150 to 200 CFM per linear foot of hood length. That is a typical design number, which means like if you've got a 1 foot hood, which nobody has, you exhaust 150 to 250 CFM. If it's a 10-foot hood, you typically see between 1,500 and 2,000 CFM of total exhaust. As you get up to medium duty, you get into hot appliances that operate hotter. You have to increase the exhaust air proportionally for that linear feet of hood. As you get into heavy duty, it's even higher. And if you get to extra heavy duty, which is like solid fuel, cooking with wood and things like that, you get a very high CFM airflow. Now, the reason for that is as you cook at a higher temperature, the plume that comes off of the food you're cooking is a lot more explosive. The water is boiling at a higher temperature. So if it's steaming, it tends to rise straight up. If it's at a higher temperature, it tends to expand very fast, which is why you need the higher airflow to help capture it so it doesn't spill out of the hood and make sure it stays within there. So these numbers and these classifications were actually developed by UL and are part of some of the listings of specific cooking equipment. Next slide, please. You can't put different appliances, duty appliances, under the same hood. And I could show you a submittal that has some of that later. What you can do is you can also separate them and put them under different hoods. This is just an example where I've shown them under different hoods, different duties. And the reason you may want to consider doing this is because of energy efficiency. First, cost-wise, which a lot of people only look at, and this is where I'm getting into where you may want to look into hood selection if you're trying to create a food service installation that's very efficient. The natural inclination is to put one big hood over all of this piece of equipment. Lower first cost, simple, one fan, easy, good to go. If you put them under separate hoods, you can now have a lower exhaust rate overall, and you can have better control. For example, on the medium duty, you could put demand control ventilation, and you might not be able to put it under the heavy duty because heavy duty equipment tends to have such high heat rates that the demand control ventilation never really goes down in speed. It just never sees that opportunity to go down. And I'll explain a little more about that later. But this is an example where you can put everything under one hood, but it might be advantageous to put different appliances under different hoods. Next slide, please. Here's an exhaust hood submittal. I've broken it apart and shown some of the parts to it that you should see in a typical exhaust hood in the submittal. As you can see, you should have the appliance lineup. You might have different appliances. For this specific one, it was decided to put two different hoods, even though they're connected back to actually operate as one hood. That might have just been for shipping reasons, getting it in the door reasons. Could be a number of reasons. But what you're going to see is, first of all, you're going to see that the hood supplier has taken into account that there are different appliances and their location, because the different appliances will require a different amount of CFM for exhausting based on duties. And also, even the location can impact. If you've got a high heat producing appliance in the middle, it will impact the amount of air you need to exhaust if you were to move it, say, to the end. One of the research projects our committee was in charge of found that out. That was a very interesting find. So your typical hood supplier has their own proprietary software based on their own hoods, because while all hoods look the same, there's a lot of subtle differences that go into how their hoods operate, whether there's little bends here and there, all kinds of little design details. So what you want to do is you want to make sure that whoever picks the hood takes it into account and has the proper appliance lineup in the proper order. And then if you go through and you look at this second column here for the specifications, you'll actually see that it's a bit of an eye chart, I understand, but there's actually a different CFM per linear foot based on the two sections of hood because there's different appliances underneath. So just because you have one hood serving appliances doesn't mean it's going to have the same CFM for whatever appliances they put into it. A good hood supplier will custom design their air CFM based on the appliances that are underneath. Go ahead, Jason. Oh, yeah. One final thing is side panels are a great option for reducing the amount of airflow. You can, if you're ever looking at a project and you want to save energy, ask if they've considered putting in side panels and how large of side panels they can put in. They cost a little bit extra, but they really save a lot of energy. They can help with the design if for some reason you're not capturing. They can help fix a problem. Go ahead, Jason. Just some quick pictures here of some typical food installations with the exhaust, with the overhangs. The equipment should be set back. They've got some side panels here, so they could probably expand out a little bit, but they may also put them on there just to reduce the airflow. Putting on side panels is not necessarily only just so you can cram in more equipment underneath the hood. You can actually drop your airflow and save energy that way. Go ahead, next slide, please. So for optimizing the hood design, talk to the owner, make sure you understand what their priorities are. If it's first cost, obviously the less expensive hood is the option to go, but if they're really interested in saving energy, and restaurants are great opportunities for saving energy, especially on the air side, you may want to investigate and work with a food service consultant to choose a better hood system that can save energy. Don't settle for canopy hoods necessarily. Back shelf hoods can save a lot of energy. They sit lower to the surface of the cooking equipment. They cost more, yes, but they can save energy. So get involved with the kitchen designers. Go ahead. Thank you, Jason. I'm going to jump into codes and standards really quickly here. And Jason, if you have any thoughts, please jump in. Typically, these are the codes and standards that are involved with any that you need to be aware of with any CKV design. NFPA 96 is a standard for fire protection. Many jurisdictions adopt it as code. It primarily deals with clearances and fire safety. It doesn't get into so much of the kitchen comfort in some of the other areas that other codes and standards evolve. I've sat on that committee. It is primarily populated with fire insurance and firemen who are concerned about fires. The best comment somebody made at a committee meeting about a kitchen is it's a contained fire that's just waiting to spread. That's how firemen view kitchens. And so that's why if you look at NFPA, it's all about fire protection. Some of the other standards are UL 710, which is the standard for hoods. 1046 is for the filters in hoods, which their primary role is to keep fires from spreading into the ductwork. They do filter out some grease, but that's our primary responsibility. And UL 300, which is for the hood's fire suppression system. Hoods usually have their own special chemical suppression system. They don't use water. Water wouldn't work well on a hot vat full of hot oil for obvious reasons. So that's why they have a special chemical for it. IMC, in addition to fire safety, they address the building and its occupants. That's where you get into some of the thermal comfort issues that Jason was talking about earlier. And there's other areas in there that you need to be aware of in addition to just the fire safety. A lot of NFPA 96 is mirrored in IMC. And in fact, one of the committees that, or one of the responsibilities that TC 510 has is we have a liaison with IMC, and they're always looking for what code changes should we implement? What should we propose to the committees as the latest and greatest codes? So one of the other, that's just a little bit of knowledge, but that's where some of these code items come from. Not everything we propose makes it, and not everything that makes it into the latest edition of IMC was reviewed by us, but we do have some input there. Getting into the ASHRAE standards, 154, that's the committee Jason and I talked about. It's ventilation for cooking, commercial cooking operations. There's a lot of great information in there. 90.1, you're all familiar with energy requirements. They've got some requirements regarding the use of hoods as well as demand control kitchen ventilation. 89.1 has some additional, more stringent requirements, whereas I think 90.1 has requirements for DCKV if you've got more than 5,000 CFM of exhaust. 189.1 requires DCKV for hoods over 2,000 CFM, so it's a little more stringent. And then finally, 62.1 is a good reference because if you're using replacement air in your building, there's some criteria regarding where you can pull it from and what you can do with it. One item I want to talk about, and it's asked repeatedly, is duct velocity. this goes into one of the research projects ASHRAE, the TC510 led, which was to determine what is the optimal duct velocity. What can you drop it down to? And the history behind this was when the committee was looking at demand control ventilation, the challenge is that if you drop your airflow when you have no cooking, your duct velocity is going to decrease. It's going to drop below the 1500 feet per minute, which was by code. So in order to have the opportunity for DCKV to be implemented, they proposed research to determine how low you could go with that exhaust. Interesting fact, nobody really knew where 1500 feet per minute came from. Somebody probably just thought of it at one time as a good velocity, and that's how it became codified. So they, as part of the research project, they retained the University of Minnesota to conduct research, and they started at 1500 feet per minute. They had a test cooking device which created grease, and they measured it, how much it deposited on the side of the ducts. And they started at 1500 feet per minute, and then they dropped the airflow, and they kept dropping it, and they measured the deposition, and it didn't increase. And they got it down to 500 feet per minute, and it still wasn't increasing any more than 1500 feet per minute. The only reason they stopped at 500 feet per minute is because their test apparatus couldn't go any lower. So I believe there's some concerns from code officials as to dropping it below the old number of 1500 feet per minute. The answer is you can safely do it, and you could probably drop it below 500, but nobody has research to back that up. Finally, at 500 feet per minute is the lowest recommended for DCKV as for designers, because you have information to back that up. There are some exceptions. I wouldn't recommend dropping it below 1500. These are listed in the handbook, but it's been recommended that if you have solid fuel cooking, that you still maintain it at 1500 feet per minute. Jason, do you have anything you want to add or any thoughts on this?
The couple things I would add is I think the 1500 feet per minute actually came from an industrial hygiene guide, and moving oil through some sort of exhaust ductwork, and so they just kind of carried it over into commercial kitchens, which, cooking grease and lubricant are not quite the same thing, which was one of the reasons why we wanted to do this project. The other thing is, I would say that, we know that a majority of the country operates under IMC. My recommendation to any design engineer is make sure that you know all of these codes, because there are some practical applications in the other codes that might not fit into IMC for either, code cycle reasons or political reasons or whatever the reason may be with the IMC. And so, and there's also some design guides out there that provide a lot of good information, and which is kind of one of those reasons why ASHRAE is taking this design guide on, is to kind of pull all this information into one source, as opposed to having the design engineer try to look through 20 different things.
Very true. I guess next slide. We'll talk a little bit about space pressurization. And I can show some examples here. I'll let you read the slide, but basically what you want to do is you want to make sure that all the air goes from any other, if you've got a food service facility within a larger building, make sure that the air is transferred from those areas into the dining room, and then transferred from the dining room into the kitchen. And the reason you really want to focus on that is for odor containment. Obviously, you're cooking food in the kitchen. Even when it's under a hood, when you pull it off, it's still cooking somewhat and producing grease. So you don't want those smells to spread around. So ideally, you'd want to have the dining room more positive than the kitchen, and the rest of the building more positive than the dining room. So kind of it transfers into there. That said, you still want the overall building to be positive. You don't want to have air infiltrating into the kitchen from if the kitchen's on an exterior wall. If you've got a freestanding restaurant, it's still the same approach, except you don't have another area of the building. You've got the dining room more positive than the kitchen, and the whole building should still be positively pressurized. I have down here hospitals may be an exception, because one of the things, the items the committee has recently come across, is that hospitals are not wanting the kitchen to be more negative than the other areas. In fact, they want it to be positive, and their rationale is that they don't want pathogens going from the other areas of the building into the kitchen, which makes sense. Honestly, I don't have an answer or an approach to do that, but it's just one of the examples that there are exceptions to the rule, and that it's one of the areas that the committee is looking into to come up with a statement or some guidelines on best ways to approach that. Next slide. Just a quick diagram of what to design for. The numbers are just kind of for a typical example, but you basically want to have your dining area more positive than your kitchen. This diagram is right out of standard 154, so you can look it up there. Next slide. A little bit about demand control kitchen ventilation. We title it DCKV, so it's not just demand control ventilation, which is more driven by CO2 levels within a space. It is a technology where you vary the cooking exhaust based on the amount of cooking taking place. Sounds simple, but it can be a bit tricky to get to work. I'll talk a little bit about how some different systems operate. It's a technique or an approach that can save a lot of energy, especially in a climate like Chicago, where you've got a lot of cold temperatures. I know we have hot summers and you save some energy in the summer, but the energy savings for these systems really shows themselves during the winter and the colder weather. There's some different ways of doing this. Different suppliers have different systems. Sometimes it's just a simple temperature between the duct within the hood and the space temperature. Sometimes they've got some smoke sensing. Sometimes they've got a little more sophisticated systems. And if you go to the next slide, there's some graphic example. I'm sorry. The next slide just has a typical example of demand control ventilation, how it operates. The slide at the picture on the left is when it's full load, you need 6,000 CFM of exhaust. When there's no load cooking, which means things are just sitting idle, say in the middle of the afternoon or between breakfast and lunch or after dinner, you can turn the amount of outdoor air down because you're exhausting less air and save a lot of energy. If you go to the next slide, then that has some examples of some different systems. The most basic system is the one shown on the lower right, which is where you use a duct sensor and then a room sensor. And if the temperature in the hood gets to be too warm, it will speed up the fan to a higher speed. And then if the temperature differential, they approach each other, which means the cooking equipment is off or not really being used, it will drop the fan down to a lower speed. The next system, which is in the upper right, is more of the duct sensor and smoke detection. Those systems react, they can have a little bit quicker algorithms within them, because if they're not detecting smoke or heat within the hood, they will tend to ramp down quicker. Comparing it to the duct temperature sensor, usually there's like a 20 or 30 minute runtime whenever it goes up to full speed. When you get into the more sophisticated controls, they can ramp up and down quicker based on demand rather than having a set algorithm which runs them for a minimum amount of time. Or I should say the minimum amount of time can be shorter because they've got better controls. And then finally, if you look at the system on the left, that's a very sophisticated system where it looks at the appliance fuel being used, as well as having some sensors that can sense when cooking is being done using infrared sensors. Those can drop the airflow quite a bit lower than the other ones and can react quite a bit quicker. And in fact, what they will do is, rather than have a low and high setting, which is typical for maybe the other two, this will have a more intermediate setting and will ramp things up and down. So the systems are more expensive. They're more sophisticated, but they offer a better level of control. So when the DCKV system is being picked out, it would help to do a bit of a financial analysis to determine if the more sophisticated system will have a better payback. Don't just have somebody pick one arbitrarily based on low first cost, unless your customer just is looking at low first cost. Go ahead, the next slide. And that kind of wraps up that section. And I guess we can open it up to any questions if anybody has any.
Yeah, we do have a number of questions that I'll start off with. I think you mentioned this briefly, but is there any specific dimensions that the hood should be at from the appliances that are under it?
There's some, as far as from the dimensions, they just have to overhang 6 inches minimum in each direction. If it's an island hood, it's got to be 6 inches in all 4 directions. If it's canopy, 3 of the directions. Sometimes they put appliances in a corner and then you only need 2. If you're in a corner along a non-combustible wall, you can put the appliances right up against the wall, although I'd recommend there be some stainless steel to keep them clean. As far as a height dimension, typically what I've seen is that they install hoods at about 6 feet 6 inches off the floor for canopy hoods. If you can install them higher, but the hood supplier needs to take that into account when they do their airflow designs, because the higher the hood is, the greater it will have to exhaust to capture. Actually, the lower you put the hood to the equipment, the more efficient it's going to be, the less air you need, which is why if you look at back shelf hoods, which are located fairly close to the equipment, they work very well with very little airflow. I hope that answers that question.
It was pretty detailed, so I'm going to say yes. We've got one about how do you verify a hood's heat capture versus it just passing the UL 710 test, which is just capturing a smoke plume? Is there another test standard? And part of this, I think you might discuss a little bit more in the commissioning section, but.
Yes, and that's a great question, because a good hood supplier will have done some of their research in the lab to determine that they are capturing all the heat and not just the smoke. There are several instruments and techniques they use for doing that. I've witnessed some of them. I've got some pictures of a device called a Schlern imaging camera, which actually, you can look it up, but it actually can detect air currents. And you can see if the heat is leaking out of the hood or not, even if there's no smoke. Another technique that they've used, it's a little simpler, is to use either a whiteboard or dartboard, where you are cooking and you darken the room, you put in a whiteboard right next to the edge of the hood and shine a light on it, and you can kind of see the air patterns if they're distortion from hot air leaking out of the hood. The Schlern is great because you can easily see it. The whiteboard and dartboard you can see, but you can't really photograph. Whereas a Schlern you can take pictures with and share. So a lot of the hood suppliers that are very sophisticated use Schlern to determine that. And what they do is they do a lot of experimentation as to how much air it takes to capture all that heat with the different appliances. And they've developed their own algorithms to come up with what should work. As far as a field way to verify that, you can do some anecdotal tests, maybe feel around if there's heat coming off of it. There's not really a foolproof way to do that. You just have to observe and see if the heat is spilling out. So I hope that answers that question.
Yeah, and we have a number of more questions. So where can we find or see the hood study on the appliance locations? I think you mentioned this in the earliest slides.
I don't know the number off the top of my head. It's on one of the earlier slides. It can be downloaded off of ASHRAE. If you're a member, I think you can get it for free. Let me get back to that question by the end of the presentation. It's a great presentation. It was done by a person who's on part of our committee named Rich Sorzina, who's probably has forgotten more about hoods than the rest of us combined know. But it was a very interesting research project because he discovered a lot of interesting parts, such as the appliance location overhangs. Even they had some issues with Coriolis effect with some of the effluent spinning a little bit, which they feel was based on a bit of like a tornado effect. But that was it's a detailed research paper that a lot of, I believe, hood suppliers took into account when they were determining their algorithms and how to size their hoods.
We just had a comment. Rich jumped in and said RP 1202.
Yes.
Thank you, Rich.
Yes, thank you, Rich.
So then our next question, I'm going to kind of pick from a couple. So can you talk about the Chicago Code kitchen hood airflow requirements compared to the UL listed airflows? And then, there was a comment that City of Chicago is still requiring the 1,500 feet per minute duct velocity right now, as we're not yet following IMC, and they have not made any changes to that yet.
I don't know. Do you want to add any comment to that, Jason? I'll just comment about the 1,500 feet per minute. Is there's science backing it up, and it's been out in the codes for. It was adopted by NFPA in about 2003, and it was adopted by the IMC shortly thereafter, and the UMC and some of the other standard codes. It's a safe. If there was any safety concerns, I think one of those codes would have flagged it early on.
Yeah, I know that the city of Chicago has an arbitrary plus 20% onto the UL number that you get from the manufacturer, which is kind of it's kind of like a CYA kind of approach to it. Unfortunately, I'm not involved in the next writing of the Chicago Mechanical Code, so hopefully, fingers crossed, there's some more, a little more common sense to the new code.
And if I could tag onto that, I think the reason why they put that in there is because people were operating their hoods at the UL numbers, which they're low. They're for the best case scenario. And typically you have more appliances under a hood than you would have. And you'll typically run your hoods higher than the UL number, unless the hood was specifically designed for that specific appliance, which some of the big chains do. So I think the city put that in there because people were operating their hoods at UL numbers, which they really shouldn't be doing. They should be doing it per the supplier's recommended airflow for that specific appliance layout and design.
And I will add that 20% was also because the Chicago numbers, if you design the hoods per the requirements in the code, are much, much higher than even the UL plus 20%. So I feel like it was a way of compromising a little bit.
Yeah, I'd probably agree with that.
Mm-hmm.
All right. This one is in a little bit of a different vein, but what are your thoughts for more industrial food service facilities and pressurizations? Aiden has been told to keep kitchen areas positive to the offices and corridors, etc., to prevent contamination from entering the kitchen, specifically for food services that ship to final destinations.
That's an interesting question, because that is a different approach too, is to keep the pathogens and everything else out of the kitchen area. And it goes back to some of the concerns the hospitals have for that reason. If that is the requirement, then that makes sense to keep the kitchens more positive than the surrounding areas. Realizing with the caveat that you're going to get all the odors from the kitchen infiltrating into the rest of the office spaces and all the surrounding spaces. So if that's acceptable, then that can be done. It isn't the one thing I would caution about, and I'd have to look at this to make sure, is that you don't violate any 62.1 requirements. I believe, and I have to look this one up, that transferring air from kitchens to other spaces needs to comply with 62.1. Probably the way around that is to put some kind of an intermediate space, something like a vestibule or something, where it would be the air from the kitchen could work its way into the vestibule, as well as the air from the office could work its way into the vestibule, and they'd never really meet. But at the same time, you wouldn't have any infiltrating air coming from the offices into the kitchen or in the other direction.
Great, thank you. These next ones should be relatively quick. Are balancing dampers allowed at the commercial kitchen hood?
only if they are installed at the collar of the hood, and only if they are listed for that application. And I may correct myself, there might be balancing dampers that are listed to be installed in kitchen hoods, but they have to be listed for that specific application by UL.
Yeah, Frank, there are some manufacturers out there who have UL listed dampers that are allowed to be installed downstream in the ductwork as well. So the key obviously is that they're accessible and maintainable. And if you're doing a design system where you have a manifold hood, there's really no way. So you have 3 or 4 hoods on one fan system. There's really no way to balance those hoods without dampers.
Mm-hmm. The key here is the reason they don't like balancing dampers in hoods unless they're UL listed and they're accessible is because they will build up with grease and become a fire hazard. So if all the right precautions are taken to prevent a fire hazard, that's really the key for why they don't want balancing, why they have these requirements around balancing dampers.
Great.
Yeah, and I think we've written language into 154 now where those dampers have to have access panels before and after. If they're downstream in the ductwork, that they have access panels before and after the damper for cleaning purposes.
Great, thanks. We still have a few more left. So are there any accommodations made for seismic design for kitchens, say in hospitals?
I don't know is my honest answer.
Yeah, I would say that on a canopy hood, I believe there are seismic requirements as well. In obviously tornado and hurricane areas, there's requirements for fans and roof curbs and stuff of that nature. So and the ductwork, obviously, if you have a welded ductwork system and it's swaying, you're going to have some compromised welds possibly. Although usually the weld is the strongest part of the ductwork. But you know, obviously there's the standard anti-sway requirements that they would have on any kind of piping system for that.
Great, thanks. The next question is, are there better or worse shapes of side panels?
For capture, the larger is better, but what they have found, and this is a little bit counterintuitive until you see how it actually works, is that the triangular panels work very well, because usually when a hood doesn't capture, the smoke will come up the back wall and will leak out the sides before the bottom of the hood. So some very small triangular side panels that are located against the wall at the back of the hood on both sides are very effective, a lot more effective than you might think. And putting some small panels will have a huge difference, and then putting larger panels will still gain you some improved performance, but not as much as those smaller ones. You get your biggest bang for the buck for the smaller panels near the back wall. Once again, a good hood supplier will be able to talk you through this and show you different scenarios as to what is the best side panel design for your application.
Great, and we've just got 2 more. So Mohammed is joining us today, and he's a grad student. And while he was working in Dubai, they would use an ecology unit to extract the air. And then, so he wants to know your thoughts on electrostatic precipitators within an ecology unit, because without using an efficient filtration system like ESP, the odor or grease cannot be removed. I don't know if that's anywhere else in your presentation or if you want to talk about it now.
I'll talk about it briefly. Ecology is a brand name, but there's a section in the handbook chapter that talks about odor and grease removal, and electrostatic precipitators pull out particulates, which do contribute to odor, but they don't remove all the odor. there's a number of different technologies for removing effluent, cooking effluent. They all have advantages and disadvantages. The only one media that removes the odors are carbon filters, which work very well, but they have a very tough life in a cooking application. They load up very quickly. Oftentimes I'll have a number of filters before they have the carbon filters to help pull some of that stuff out. So it won't be one filter, it'll be a number of filters typically. So they do work, but they require maintenance, sizing, they require their own fire suppression system, and they do add costs. So you want to make sure that you really need them. Any thoughts on this, Jason, that I haven't covered?
No, I think you pretty much hit everything on that one.
Great. And then this next question, I think, is pretty leading into the next section that you're going to discuss. But what rate of makeup air should be provided from a makeup air system versus what percentage of air can or should be transferred from adjacent spaces or cooling systems in the kitchen?
Are you going to cover this in your next section, Jason, or do you want to?
Yeah, I won't get into those specifics, but generally, I mean, rule of thumb is kind of a 50-50 split. So it's 50% makeup air to the kitchen and 50% transfer air. If you can do it in your design.
Great. That was our last question for now. So I'll let you continue. Thank you, Frank and Jason.
Thank you, Liz.
All right, let's get into some replacement air information here. Replacement air, makeup air, they're kind of used interchangeably. We've tried to use replacement air in terms of we exhaust air and now we have to replace it with more air. So that's the term replacement air. Generally, there's three options for providing replacement air into the kitchen. So into the room, which is pretty much your best option. You can do this via displacement ventilation systems or ceiling supply. I know displacement ventilation really isn't a viable option in a lot of kitchens. Probably more when you get into some of the, if you do industrial cooking applications, displacement ventilation may be a good option for you. And it's most useful since the air can provide some cooling to the space as well. At the hood is a good option. Sometimes it's necessary to take that approach. One example is perforated supply plenums. Those come in different variations. We have front face discharge, down discharge, and in some cases internal discharge. What we call internal to the hood. We typically don't recommend that application. It's commonly referred to as a short circuit hood, and your replacement air in that application is limited to 10% of exhaust. And for any percentage of makeup air over 10%, you have to increase the exhaust CFM. So anything above 10% makeup air into the hood can drastically impact the hood's ability to capture and contain. It actually ends up blowing the exhaust air out of the hood and the grease and the vapor and everything else. And if you're using conditioned air, then there's really no benefit in providing air into the hood itself. All right, so we know the International Mechanical Code has some rules around makeup air temperature, typically within 10 degrees of the conditioned space, except where the added heating and cooling loads of the makeup air do not exceed the capacity of the HVAC system. Translation is the replacement air is exempt from tempering so long as the comfort, cooling, and heating systems can compensate for that additional load. All right. I would recommend avoid using that exception. It can be problematic, and recommend definitely just tempering at the source. Why can it be problematic is if we're bringing unconditioned air in and it's a front-facing supply, all of that replacement air now is going into the kitchen untempered, unconditioned, and humid, and potentially causing condensation on diffusers in the kitchen and resulting in some potential health code violations if we have condensation dripping on food. So just one of those things to be aware of. If you're in a dry climate that doesn't have humidity issues, then that's a different story. But for the most part, I would recommend staying away from that approach. All right. So as Frank mentioned, these are some images of Schlieren taken from the side of the hood. The front supply with too much air being supplied can cause spillage. So you're seeing this on the first picture on the left, and there are requirements for what that air velocity is and what that air velocity needs to be at the face of the hood. The internal supply in the middle picture, with too much air being supplied, again above that 10% limit that's been set. You can see at the outside of the front of the hood, even along the face as it goes up towards the ceiling, that spillage, that heat spillage coming out. And then last but not least, the third picture, the front supply operating as intended with no spillage. All right, so you'll see with the front supply, it's actually raised up higher from the face so that we can meet that velocity requirement at the face of the hood. All right, so again, we have a poll question here. Just by doing a raise a hand raise in the GoToWebinar application, the question here is, when you're not using tempered supply air, are you accommodating for that heat gain in your HVAC load calculations? If this was an anonymous poll, I would probably, not be concerned about it, but I don't think anybody actually wants to admit to not doing this. Could be wrong.
But it also means that they lost the battle of tempering the air coming into the space.
Right, yeah. I mean, guaranteed uncomfortable kitchen.
So we've got about 9 people that have risen their hands.
Okay. All right, so they're accommodating for it, which is good.
Mm-hmm.
We'll take that. All right. So I'm going to show you 3 scenarios of a CFD model of a countertop appliance. It doesn't really matter what the appliance is: toaster, charbroiler, fryer. Surface temperature is substantially higher than ambient, typically, in that 450 to 600 degree operating range. And so this model shows appliance under a canopy hood with a supply plenum that discharges downward. All right. So make note also that CFD models only show convective heat. They don't show radiant heat in this particular application. So that's another thing to consider. A lot of these appliances have a pretty substantial radiant load as well. So in scenario 1, this is what I call heated in the winter or not tempered in the summer, right? So we know that the air coming into the space is substantially higher than the space temperature ideally should be, around that like 75 to 78 temperature range. So what we find is, due to the buoyancy of the warm air entering the space, about 50% of the hot air goes back into the space. So now we need to accommodate for that 50% additional load going back into the kitchen. All right, so we need to make sure that we're accommodating for that. The other thing is, what about the person that works here, right? If we have a hood mounted at about 7 feet high, where's this person's head going to be, right? It is right in that hot plume, okay? Not really where you want to be working, okay? So imagine being the cook. They have to stand in this hot plume for several days out of the year. And so I asked the design engineering community, how are we providing comfort for building occupants when we design ventilation like this? And I would argue that we are not. So let's go back to item 1, where I said 50% of the makeup air goes back into the kitchen on a down discharge application. So if we have front face supply, 100% of that heat gain pretty much goes to the space. Okay. So again, depending on how you're bringing in that makeup air impacts the comfort in the kitchen. All right, so this is scenario number 2. All right, this is when the supplier temperature is too cold. So we're bringing in temperature at around, it looks like around 50 degrees in this particular model. All right, you know, not bad. I mean, if you're a cook, this might not feel too bad. A little bit of cold air blowing on the back of your neck while you're working in front of a hot flame. You know, this application, maybe we're using a rooftop unit or a DOEAS unit for the plenum supply. Maybe we didn't use a discharge temperature sensor to operate the makeup air and guarantee that this is coming in at a reasonable temperature. So what we see in this model is that the cold air makes it all the way, almost all the way to the floor, right? If there's any type of moisture rolling around in the front of this hood, there is the potential for pulling grease and water out of the airstream and having it condense. All right, if the conditions are right, you know, and potentially even accumulate grease on the floor, and obviously that would be a slip and fall hazard for anyone working there. So again, let's bring in our chef. You know, like I said, the head's right in the 50 to 55 degree temperature range. Probably not too bad for the cook. You know, but again, the condensation potentially forming on the cook's clothes and skin, maybe not a good thing. Sounds kind of gross if you ask me. If you got grease condensing on your skin. All right, so here's scenario number 3. This is space neutral supply air temperature. All right. We have no hot plume. We have no heat gain to the space. All right. Best way to keep the workers comfortable. All right. This approach ensures that we have good capture and containment. It doesn't add heat to the kitchen, like I mentioned. Creates a more comfortable environment. And if we look at our chef as they come into view, he or she would be probably more than happy with a 75, 76 degree temperature space, working in this type of environment. All right. Happy employees means better retention. All right. So for those of you that don't know, restaurants have one of the highest employee turnover rates in the industry. And it's partially because of, one, the stress, and then obviously the comfort conditions do play a role in that. All right, so we're gonna play a little game here, and it's called "What's Wrong with This Picture?" Now, normally this would be a little more fun in person, but I'm gonna start with a couple quick ones here. Right, we know as HVAC designers that it is bad practice to have a return diffuser located pretty close to a supplier diffuser. In this kitchen or this food service area. The return diffuser is literally one ceiling tile away from the supply. All right, so now we've got a short circuiting issue. That's a design 101. So the other thing that is probably a little bit lesser known, unless you've designed a lot of kitchens, is we have four-way diffusers in the ceiling, all within about 10 feet of this hood. All right. This is just it's really poor kitchen design, and having the diffusers within that proximity of the hood actually pulls the vapor, the grease vapor, and the moisture out of the hood, and does not allow it to capture and contain properly. All right, so generally the simple rule is do not place four-way diffusers within 10 feet of any hood. All right. I'm going to take that a step further. I'm going to cross that out, right? My recommended rule is do not use any directional diffusers in a commercial kitchen. Right, that includes plaque diffusers, louvered face, square cone, perforated diffusers with guide vanes in them. And I'm just gonna use this as a reminder because it bears repeating that no directional, just don't use directional diffusers in the kitchen. All right, the less air turbulence, the better. Okay, the calmer the air the distribution is, the better the hoods perform. You know, and I asked that question to the beginning of the poll, one of the poll questions about designing clean rooms, and you're going to see why it's very similar, and how good kitchen design is similar to designing a clean room.
Hey Jason, sorry to interrupt. I just wanted to let you know we're at 6:15 right now, so we officially have 15 minutes. We can go a little bit more, but want to make sure you guys focus on the things you definitely want to hit on.
Yeah.
Thanks.
I'll kind of skip through some of these at a high level. So, you know, if we're not using directional diffusers, what are we using? I'm gonna show you three types here really quickly. Option one is the perforated return diffuser, and I say return, which sounds odd. Why would you use return for supply? Well, there's no directional vanes in a return diffuser. All right, so in this scenario, there's a plenum that gets built on top of the diffuser. This one is a 2x4, and then it has a side entry on it. There are a couple chains, restaurant chains out there that use this style of diffuser. The obvious one, clean rooms, laminar flow diffusers, very simple. They come in different designs from different manufacturers. And the nice thing about them is that they, you know, have a top entry, which, you know, is a little bit more common for some of the contractors out there. And then the third option here is what we call the fabric diffuser. I think there's only maybe 2 manufacturers out there that make something of this nature. Probably your least expensive option, has a top connection like the laminar flow. It's easily cleanable. You can take off the fabric and throw it in a washing machine. But aesthetics are a concern. It does, you know, hang down from the ceiling. I call it the pillow, so to speak, and it can obstruct some views. If you have a restaurant that has monitors in the kitchen that are used for creating orders and stuff and whatnot, the diffuser can potentially obstruct the view of those monitors. So highly recommend that you talk to the owner before you ever specify this type of diffuser. All right, so here's an example layout on a restaurant that I worked on a couple years ago, and this uses the 2x4 with the shop fabricated plenum on top of it. The nice thing about this is proximity to hoods is of little concern. If you space them out pretty evenly throughout the kitchen, you have a pretty comfortable kitchen throughout. There's not a lot of complaints about comfort. And then my recommendation is limit the face velocity of the diffuser to 200 feet per minute. It's considerably less turbulent. In this particular design, we were about 150 to 170 feet per minute, depending on where the air balance came back. But the nice thing about this design is that pretty much no matter where you stand in this kitchen, you're going to be comfortable. All right, this was a fully air conditioned system. There's no makeup air at the hoods themselves. This is all distribution throughout the kitchen. So again, kind of going back to that clean room question that I asked before, if you ever design a clean room, the ceiling looks very similar to this. Each one of those gold rectangles represents a diffuser in the ceiling. All right, I'm gonna take a break for questions.
We just had
flew through that pretty quickly.
We just had a couple quick ones. What is the acceptable design temperature ranges that you see for commercial kitchens? And I'm not sure if this was temperature of the makeup air unit or in the actual space itself.
I'm going to assume that's in the space itself. I say strive for 75. It's kind of a nice little catchphrase. But the reality is that you're probably not going to hit it. You know, 78, 80 degrees is probably okay. Maybe low 80s, but beyond that, I wouldn't go much higher.
Great. And then we just have one other question relating to designing the makeup air handling unit. Should we use a configuration of something like a heat pump to decrease the amount of dehumidification?
Yeah, I mean, I think a heat pump is always a good option.
Or heat
You know,
pipe.
doing,
Sorry.
you know, heat pipe system.
Yeah, sorry.
Okay. You know, makeup air. I mean, you can use whatever you see fit. Typically, I've used OAS units with hot gas reheat. Is kind of my standard practice.
I've seen that as well. All right. I think that's, let's see. Yeah, Mohammed just had a couple more comments on his question, you know, with the wraparound heat pump, and it would be best with the high fins to reduce the dehumidification. But yeah, I think we're going back to a lot depends on where you're putting this unit in,
Yeah, right.
climate and all that.
Yeah, application and climate specific. You know, used again, you know, makeup air units with 6-row coils. I've used those. All depends on where you are and how much money the owner wants to spend and everything else.
Mm-hmm. Great, thanks.
All right. Okay, so gonna kind of try and cruise. We got about 10 slides left and about 10 minutes left. So hopefully we can get through most of this at a reasonable pace without a whirlwind of information and you guys scratching your heads asking what's going on. So we're gonna talk really quickly about appliance heat gain and why it's critical for creating comfort in a commercial kitchen. So this is a breakdown of load percentages for a restaurant I worked on. This is actually the same restaurant that I just showed you that ceiling plan of. You know, it's important to note this is a pub style restaurant, so there is some dishwasher and refrigeration load out in a couple bar areas outside of the kitchen. So you'll see that I broke this out into the cooling load for the whole building versus the cooling load for the kitchen only. So the kitchen did have some exposure, but it wasn't a lot. From a whole building perspective, we're looking at about 20% of the heat gain in the spaces from appliances. When we look at the kitchen only in this particular application, we're looking at almost 33% of the heat gain. The other one is the ventilation, obviously, with makeup air requirements being what they are. This is why critical. This is why reducing your exhaust requirements is so critical to energy efficiency in a restaurant. There's a direct correlation with energy usage and ventilation rates up to a certain point. If you get them low enough, then it kind of shifts into some other things. But for the most part, ventilation is the major cause for energy usage in a restaurant. All right, so I'm just going to run through a quick project that I did. This is a restaurant that I worked on last year. It's a little bit different because there's no cooking. Everything is, most of the food is pretty much raw, except for in the back, they do have a combi oven with a recirculating hood that is used for kind of warming bread and baking croutons for salads and stuff of that nature. There are only 2 areas in this restaurant. It's relatively small, around 1,200 square feet. And we have a front counter area and a back of house area. All right. Before we even got started on it, we met with the owner, and they have multiple locations in the city. And they came back to us, and the first thing they said is they have comfort issues at basically every single one of their locations. All right. So we'll get into why that is in a little bit, but a lot of that obviously has to do with the appliance heat gain. So before we even ever get into load calculations, we gather a complete equipment list of everything that's going into this restaurant. All right. We put it into a spreadsheet, and we add some columns in here. You'll see it's a little bit of an eye chart. I'm not expecting you to read it at all, but there are five columns that we add. The appliance location, so that we can sort out where that heat gain is actually occurring. The sensible heat and latent heat per appliance, and then the total and total sensible and total latent, and those totals are just a product of the number of appliances times the heat gain per appliance. All right, so it's basic math, which is why the spreadsheet really comes in handy. So on the left here is an example heat gain schedule that we made for the project. We use data from the manufacturers. A lot of refrigeration manufacturers have heat gain numbers for their refrigerators, so it's really easy to get that information from them. And then obviously we use the ASHRAE handbook, chapter 18, which we did all that research on to get the appliance heat gains and published into that chapter. So when all is said and done, the front counter heat gain was about 26,000 BTUs. I rounded some of this just to make it simple. And then the back of the house was about 43,500 BTUs of heat gain. This is just from appliances. Okay, so it can be pretty substantial, and if it's not accommodated for, this is when the comfort issues arise, right? So if we go back to the floor plan here, what do those numbers look like? This is just kind of like a high level overview. The front counter area is about 670 square feet of floor space. We from the spreadsheet, we calculated 26,000 BTUs. It's about 40 BTUs per square foot. All right. For the back of house, 43,500. The back of house area is only 550 square feet, and about 100. I included the walk-in refrigeration on this, but that takes out about another 120 square feet of that space. So it's it'd be really 430 square feet of actual occupiable floor area for the HVAC system to look at. And that comes out to about 85 BTUs per square foot, which is a pretty substantial load. If this restaurant is operating full bore in the wintertime, the heat's not turning on, right? Even in probably January. All right, so one of the reasons why it's critical that we separate these areas. Their heat gain can have a pretty big difference, and their peaks can have a very big difference. In this type of restaurant, most of the preparation is done before lunch, and then all the activity moves out to the front counter area, and then at lunch it moves back to the back of house area. So the load profile on this is very different than some of the other restaurants where peak is at lunch and everything is operating at 100% in the kitchen and in the front of house. So again, knowing those schedules obviously from the owner helps a lot. So that brings us to poll question number 6. Again, raise a hand on the GoToWebinar application. How many of you designing restaurants are creating an appliance heat gain schedule?
Oh, looks like a good number, about 12.
All right, that's good. All right. Okay, so what did that mean for the clients? Front counter versus back of house, right? So the previous project, they said, oh, we've got comfort issues. The new project, all right, so we're going to compare these side by side. I will asterisk this. The new project had north and west exposures, though the west exposure had the second floor overhangs the building by about 30 feet. So the west exposure isn't that bad, though it does have some heat gain. Obviously, the glass is not a good insulator compared to a solid wall. And then obviously the north the north side is another issue. But on the previous project, the designer had 600 CFM in the front counter area and 700 CFM in the back of house. All right, and it's on a VAV system, so it's pretty straightforward on how this works. We've all designed VAV systems for office buildings and whatnot. The new project, the front counter area was 2,400 CFM, so we're supplying 4 times the amount of air that that the previous project was. Again, some of that is due to exposure. And in the back of house, we're at 1,950 CFM, which is 2.5 times, almost 3 times what the previous project was at 700 CFM. The system design for the new facility is 1 fan powered box dedicated to each space, so that there's consistent airflow to each space. And then we added a supplemental system because the landlord would only give us so much airflow, and so we had to supplement it with a small 3-ton split system. And the benefit of that is now in the back of house, and during the hours after dinner, the building shuts down at 6 o'clock. The restaurant shuts down at 6 o'clock. Now the employees are in back cleaning up, and that is anywhere from 1 to 2 hours of cleanup, but they still have air conditioning, whereas before they don't, right, without the building, if the building turns off. Like I said, I can't stress enough how important it is to separate back of house areas, kitchen areas, and dining rooms, and make sure that they're on separate systems and never on the same system. The kitchen will very likely need cooling year round, if not 9 to 10 months out of the year. All right, we're gonna pause for some questions if there are any.
We just had one really fast comment, and that it's often hard to get the kitchen appliance lineup from the tenants prior to mechanical drawings going out to get the appliance load. Is that something that you found as well? Or I know in terms of if you're building out an actual tenant space, trying to determine what kind of provisions the base building should make for kitchens can also be difficult.
Yeah, on a base building, obviously, the building owner is going to have some requirements. It's like 1 CFM per square foot, or 1.5, or whatever their kind of empty space requirements are. And so, particularly in these high-rise applications like this restaurant was, there's almost never going to be enough airflow from the building itself. You're always going to have to supplement. And that goes for high rises, airports, shopping malls, indoor shopping malls, all those things. You're almost always supplementing the main building system.
Yes. In the interest of time, I thank you for the response. I wanted to let you all know that this webinar recording will be available. So if anyone has to jump off, as well as the PowerPoint, it'll come out in your typical email from Don. And then, so we're going to make Frank talk really fast, because not only are we passing our normal time limit, but we're not supposed to stay on this society-based webinar too far past our scheduling. So thank you.
Sorry, guys.
Move fast, Frank.
No problem. All right, next slide. We'll go through this quickly. And by the way, to answer a previous question, there is a chart in the ASHRAE handbook that has the psychrometric chart with a trapezoid in it for the comfort zone that was based on the research project. So if you're wanting to design a kitchen that's comfortable, I forget the exact table, but look in the ASHRAE handbook, chapter 34, applications. Balancing hoods. I'll do this quickly. Make sure that your air balancer follows the hood's requirements. There's different hoods have different requirements. Use different instruments. Don't make sure that they follow. If it's a velocity grid, they use a velocity grid. If it's a rotating vane anemometer, some of them have installed PO tubes where you can just plug in a quick pressure differential sensor. Duct traverse is not typically employed because you have to drill through the duct and run your PO traverse through it. The duct is fire rated usually, and everything has to be welded. There are exceptions, but for the most part, people don't typically do PO traverses for balancing hoods. It's always at the face of the filters in the hoods. Next slide. Using smoke. Smoke candles are good for visualizing airflow, and I think the question was asked previously, can you detect if heat's coming off of the hood? It might be good. A good way to test it would be putting a smoke candle right at the edge of the hood, like where the smoke candle is, except the air would be being pushed out if you saw some leakage. They don't simulate real cooking though. Same thing with smoke bombs. Smoke bombs cause too much smoke. They don't simulate real cooking. So while some people use it for occupancy, some authorities do, it is not a valid test to determine if your hood is capturing under the conditions to which it was designed. Smoke bombs might work if you're doing solid fuel, otherwise, but I wouldn't recommend them even, maybe not even that case. The actual best method is to watch cooking, which I know is a challenge because you typically cannot cook until the building's occupied and they've got their C of O, and that's typically after commissioning is done. But as commissioning, there's also warranty visits and seasonal visits. So you might want to put that, if you're commissioning a system, a visit to go in there and watch them cook when they're cooking a lot of stuff too, like for breakfast or lunch, and cooking things that cause a lot of smoke. Next slide. Some do's and don'ts. I'll let you read this, but basically it's common sense. Make sure that you're just checking everything, probably the bullet points at the bottom. I'll work my way up since they're probably the most critical. Is use data loggers to ensure things like demand control ventilation are working properly. Check the pressure and between spaces. You don't need a fancy instrument to do that. You can just stand between two spaces and maybe close the door and see if the if you can feel the air getting pulled through. When I was doing a project in another country, we used incense. That was a fun experience, commissioning a restaurant with incense, and it showed where things working and weren't working. So the next slide, which I think is the last slide for this section, the most critical part is to verify the hood has proper capture and containment during full load cooking and at all minimum and maximum flow rates if it's got demand control ventilation. Different systems that need to be tested include the replacement air interlock, so that when you turn the hood on, the replacement air works. When the appliances turn on, the hood operates. Sometimes they're interlocked mechanically, sometimes they use a heat sensor within the hood. DC KV system, make sure that that operates. It ramps up and down like it's supposed to. You can work with the supplier on that one. Ideally, it's best to go witness them doing some of their setups when the hood supplier is commissioning their system. Observe what they're doing. And the HVAC fire suppression system interlocks, that definitely has to be done with a fire suppression contractor. He'll trip his system, but in a way that it won't spray the suppression all over the place. And what you want to do is make sure that they get the fire alarm at the panel, the HVAC turns off, except probably the exhaust fan. I say probably because this is how it's typically done. When a fire suppression system in a hood trips, the exhaust fan continues to run. It's by design. It's because they want to pull the fire suppression up into the exhaust ductwork up to the fan. One thing on this picture here I want you to see, and it's very hard to see this, take a picture of it, but this hood is not capturing. You can see the smoke coming off of the food, and it's drifting to the right out from underneath the hood. There's some other issues wrong with this too, the fact that the appliance is right up against the edge of the hood instead of a 6-inch overhang, but that's why cooking is the ultimate test to determine if a hood captures. Finally, just make sure the space pressurization is maintained for all operating conditions. That's the speed presentation of commissioning. I guess we can open the floor up to questions.
Thank you. We do have a question from Mohammed that he would like to ask verbally, so I'll try to do that in just a second. But real quick before we end up, do you guys have one thing that you maybe have seen that's super crazy in your either design or commissioning of kitchens, or one thing that you think is a random thing that's extra special for us designers to be looking out for?
I'll jump in first. Hood selection and making sure you're picking out the right hood for the application and not just something that works, has energy efficiency, is really been thought through for the application. I feel like that's just the biggest opportunity in all the kitchen designs I've seen. And I'll just throw in air balance. 90% of the problems in kitchens are air balance.
Yeah, I'm just gonna echo Frank's comment on hood design and hood selection. I have made it a point throughout my career in design to kind of go back to owners and to kitchen designers and tell them thank you, but no thank you. I trying to have them design a ventilation system for the building that I needed to design a ventilation system for, just to me has never made sense. I would probably challenge all the design engineers in our community to challenge our kitchen designers to avoid hood selection if they can. Obviously, they can give you a base spec if they want to. The challenge there is they all seem to come back with the same type of hood, and maybe that's not always the best option. And there's really never been a conversation with the building owner around how energy efficient do you want your restaurant to be. All right, and so if they tell you that they want it really efficient, then your first response back to them is you need a better hood, hands down.
Great, thank you. We did have another question come in. Why do so many restaurants end up with negative ventilation rates?
Because somebody closes the outside air intake damper and thinks they're going to save energy, and it doesn't work out that way. In the name of timing, there were some slides where there's actually a picture of a restaurant, the front door, and it says pull hard because the restaurant is so negative. That's a great one. But that's the reality of it is somebody says, hey, I'm going to save you energy by closing your outdoor air intake damper. And it doesn't. Air goes into the building no matter what. We all know that. It's just going to leak in through all the doors, through all the cracks, through infiltration. And it's going to cause comfort issues as well as operational issues. And then people come in there and then they'll come in and try to speed up the exhaust fan to try to compensate for it, which exacerbates the problem.
Great, thank you. All right, I'm going to try to have Mohammed ask his question.
Hi, hi, Mr. Frank and Mr. Jason. Thank you very much for the opportunity. Well, I'll go specific into the question. It is relating to DOS system. So when we design a multi-story building with DOS system and air handling units to supply the recirculation air, can't we increase the amount of ventilation air from the DOS system? Because the amount of dehumidification required in a DOS system, it can be drastically decreased using high efficient enthalpy wheels, which would absorb the latent load from the air as well as the sensible load. So my question is, if amount of dehumidification, the amount of dehumidification, if we could reduce using the enthalpy wheel, so the amount of load would on the coil will be reduced, right? So will it be a good strategy to increase the amount of ventilation air using a DOS system?
If I understand correctly,
yeah,
the enthalpy wheel pulls works in conjunction with the exhaust. Is that correct?
Yes, I mean with heat recovery. Yeah.
Yeah. The challenge with that is kitchen exhaust is nasty. It's usually hot, and it's got grease in it, and the grease will tend to clog up the enthalpy wheel in short order. Yeah. There's ways to do heat recovery, but they have to be specially.
Yeah. 1 point. I mean, I know for the fact that we don't recover heat from the kitchen. I mean, talking in general with the spaces which are not kitchen. I mean, which are not is the general spaces, office spaces, or any occupants wherein inside a room.
Yeah, but I'm just gonna chime in here. If you're now exhausting air from the building with the energy wheel, with the enthalpy wheel, you now have to increase your makeup air or your supply air to make sure that you're still maintaining a positive building pressure.
Yeah.
Right. And so you're just kind of fighting yourself with the exhaust versus the enthalpy wheel on that end.
Okay. Yeah, and second, that's it. I mean, that's what my question is. Thank you very much.
Thanks.
Thank you.
All right, and we have one final question before we have to all jump off. What is the best way to select the best type of hood for an application? Is it ASHRAE Chapter 34 of Applications, Table 4 and 5, the best reference for that?
I will say ask a couple of different hood suppliers to submit their most energy efficient hood for a given appliance lineup and compare them. It's almost like, I'll compare it to like chillers. You know, you can look at different suppliers of chillers and they're all going to have different operation characteristics at full load and part load conditions. And you can do a straightforward costs savings analysis in that manner and do the same thing with hoods, whereas look at whose hood, how much it's going to cost, and then what airflow they're going to be exhausting at.
Great, thank you. That was all the questions. So and also resounding thank yous from our audience. Thank you so much for joining us today, taking the time as well as this great presentation. I wanted to remind everyone that the presentation will be available to download. You may have even been able to do it yourself. And then also we'll have the PowerPoint available. So check your emails for that, for the typical email from Don, as well as a quick survey. And just wanted to remind everyone, you know, if you want to get more involved in our chapter, or as Frank and Jason both mentioned, in any of the technical committees or reviewing of standards and things like that, you know, reach out to any of us, please. Frank and Jason, do you have any other parting words?
No, we could have gone on for another 2 hours with a lot of different topics.
Yeah, I mean, I actually have, it's not really a parting word per se. There was, going back to that last question that you had asked Frank about, you know, maybe like what are the things that we could recommend, or wisdom, so to speak. And I see this a lot. If you are going to use a rooftop unit in the dining room of a restaurant, and you have a decent ventilation rate on that rooftop unit, please make sure that you're adding a supplier temperature sensor and the ability to what we call supplier tempering on those rooftop units. We've all been in restaurants where we're sitting in the dining room, we're comfortable, and all of a sudden, you know, it's wintertime, and all of a sudden there's this cold air blowing on us. And what happens is the call for heating is met, the heat exchanger, you know, turns off, and all of a sudden we're getting cold air blown on us. And so what supplier tempering allows you to do is regulate the discharge temperature on the rooftop unit. And not every manufacturer has it, so just be cautious about which manufacturer you're using. And I would just say that that's probably one of the biggest design issues I see outside of the kitchen area.
Great, thank you guys so much for everything, and I think we should all go enjoy the rest of our evening as well. Hopefully we'll see how much it rained places. But thank you again. Please reach out if you want to be more involved, and we hope you have a great summer. Looking forward to seeing people hopefully in real life sometime again in the fall. So
absolutely.
Great, thank you guys so much.
Thanks everyone.
Bye.
Thank you. Bye-bye.